Good morning, BHS and CHS students. Or I guess good afternoon or good night whenever you happen to be working on this or watching this video. I figured that I would just kind of start with this little supplemental lesson talking about power laws because we're going to be doing logarithms, exponential models, and everything, and that would be very difficult if we did not, in fact, know our power laws, like what exponents are, how they work, how to manipulate them. So that way when we get into solving, this stuff will make a little bit more sense. Most of you should have already learned this, but this will be a nice little review video. I'll try to keep it as short as possible. But we've got 8 basic laws here, and I'm going to try and keep it in the color of the law that I'm working with. That way it'll make the video less confusing. If you have to navigate, that should make it easier. Anyway, so let's just talk about what an exponent is, starting with the red law here. So if you've got x to some power, I know that over there it just says 1, but I'm just talking about exponents in general. And when I do that, it means that I'm going to multiply x by itself some n number of times, and that n can be anything at all. So I can keep extending this in numbers of times. So for instance, just to make it a little clearer, if I've got x to the 3rd power, that means I'm going to multiply x by itself 3 times, right? And we can do this with variables, but we also do it with numbers, right? So 2 to the 4th power equals 2 times 2 times 2 times 2. And when you actually have them all written out like that, if you actually know the value of what it is that you're raising your exponent to, you can actually calculate it. So 2 times 2 would equal 4, times 2 would equal 8, times 2 would equal 16. So the value of this exponent, 2 to the 4th power, is equal to 16. Now, something that when we start inverting these exponents, when we start making them negative, something that I want you to keep in mind is that we can actually imagine this when we have an exponent. Say we raise 3 to the 3rd power, we can imagine this 1 out in front. So 1 times 3 times 3 times 3. We don't write it because the 1 is not going to change the value of all of this, but 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. So that 1 doesn't change the value, but it's going to be kind of important when we start looking at what the inverse actually means in these sort of situations. So just going back to what we have here, x to the 1st power is just equal to x. And that should make intuitive sense when you see how exponents work. When you've got an x to the 2nd power, it means you're going to multiply it twice. So 3rd power 3 times. When there's just a 1 up here, x is just going to be 1 times x. Just like that 1 there. So we're just going to have x 1 time. So x to the 1st power is equal to x. And that's going to be true of anything. If you have, I don't know, 862 raised to the 1st power, that is just going to be 862. Alright? Okay, so I told you to keep in mind that 1 at the beginning, and this is really the reason why. Because when we start dealing with inverted exponents, negative numbers up here, let's just start out real simple, 2 to negative 3. We talk about inverse operations in class, especially when we're talking about solving equations. And when we talk about an inverse operation, we're talking about like the opposite thing. Like the opposite of addition is subtraction, the opposite of multiplication is division, and that is actually the key here. Because if 2 to the 3rd power represents 1 times 2 times 2 times 2, the inverse, this negative sign here, this inverse is going to represent not multiplication, but division. So we'll have 1 divided by 2, divided by 2, divided by 2, 3 times, alright? And so when we think about what this actually is, 1 divided by 2, well, that's just going to be 1/2, right? And we divide by 2 again, that's going to be 1/4. We divide by 2 again, that's going to be 1/8. So when we think about 2 to the negative 3rd power, and we've got these divided by signs, we know it's going to be 1 over 8. And this 1 is kind of important just to remember that's what's going to be going in the numerator there. The denominator, and once you kind of figure out the pattern, the more you do these, the more you'll see this pattern. There's actually a much easier way to think about this. This negative sign here, all it's going to do is take whatever number is raised to that negative power, and it's going to flip it over this fraction bar. So that would be the same as 1 over 2 to the positive 3, right? The negative 3 turns to a positive 3 when it goes under the bar. So just as another example, if we've got, say, 3 to the negative 2 power, that would be equal to 1 divided by 3 twice. So divide by 3 divided by 3, right? And we know, we apply our shortcut, and we want to think about what this negative is actually going to do to this 3, we know the negative is just going to flip it under that fraction bar. So it will be 3, and then the exponent will become positive. So 1 over 3 squared, in other words, 1 over 9. And it works on the bottom too. So if I have, say, I don't know, 1 over 4 to the negative 2 power, this negative sign, instead of putting it like on the bottom, it's going to flip it over this bar, and it's going to go straight to the top. So it will become 4 squared, which is equal to 16. And I really hope that makes sense to you guys. I've been using numbers, but just if we think about the way that this works, the way that this is applied, we can use variables too. And just like it says over here, x to the negative n power equals 1 over x to the n power, we can say that x to the negative, who knows, 27th power is equal to 1 over x to the 27th power. And hopefully that does make some intuitive sense. So let's kind of move on here. Alright, let's change our color up into blue. Alright, so what this law is essentially telling us is if you have two powers that are being multiplied together, those exponents are going to add together. So if you have, say, x to the 5th power multiplied by x to the 3rd power, that is going to be x to the 8th power, because 5 plus 3 equals 8. Here, let me make that a little clearer, showing a little bit of an extra step. All right. So 5 plus 3, so that would equal x to the 8th power. And this is going to make a lot of sense, and that's the thing I love about exponents, is that you can really break these down. If you forget these laws, you can simplify them, you can break them down. Let's think about something easier to write, but let's say like x to the 2nd power times x to the 3rd power, and we all know, because of this rule, that 2 plus 3 equals 5, but let's say that we didn't know that. What is x squared? Well, as we talked about in that first law, x squared is just x times x. Well, I mean, we can put the 1 out there in front, but that's not necessary right now. And then we're going to multiply that. So this is its own group. This here is x squared. And then we have x cubed, which will make that in its own group. X times x, because it's x multiplied by itself 3 times. And when you're multiplying stuff straight together, it doesn't matter the order. So we can actually get rid of these parentheses. And what does that look like when we do that? It's just x times x times x times x times x. And when we solve this, how many total x's do we have? We have x multiplied by itself, because we're multiplying, right? Multiplied by itself 5 times. So x to the 5th power. So that is fairly intuitive, and if you forget, like, you can always just kind of break it down. But let's kind of prove this using numbers. So we'll use the same sort of exponents, and nice small exponents. Oops. Sorry, I wrote an x when I just said I was going to use numbers. So let's say that we've got 2 to the 2nd power multiplied by 2 to the 3rd power, just to prove that what we're doing, manipulating these variables, actually works with numbers as well, right? So what is 2 squared? Well, we know that is 4, and what is 2 to the third power? So 2 times 2 times 2, we know that's 8. And what is 4 times 8? Well, that's 32. Now, what we are saying with this law is that 2 raised to the 5th power is also equal to 32, and you can pull out a calculator and you can find that, but really what we can do is just walk through it. 2 times 2 equals 4, times 2 equals 8, times 2 equals 16, and 16 times 2 equals 2 to the 5th power, which is 32. So hopefully that makes a lot of sense. And the division, which, let me switch my color, is going to be very similar. And let's see. So let's just kind of like start with numbers and see how this kind of works. I want to talk about just division in general, and say that we've got like 27 divided by 9. Well, what we know from fractions, from divisions, from ratios, is that we can simplify this. This is a reducible fraction, and we can break it out into its prime factorization, right? So 27 is 3 times 3, which is 9, times 3 more, that's 27. This is the prime factorization of 27, and the prime factorization of 9 is 3 times 3. And now, once you have this in its prime factorization, what you find is that because any number divided by itself is 1, we can, like, I don't like to say canceling out, but essentially if you have a number on the top and the bottom, these will both become a 1 multiplied by whatever's left. So in a sense, they kind of, quote unquote cancel out, but that's not really mathematically speaking what's happening. So 1, 3 on the top, 1, 3 on the bottom, they cancel out. 1, 3 in the top divided by 3 in the bottom is 1, and all you're left with is a single 3 on the numerator. All you have on the bottom is just 1, so 3 divided by 1 is 3. So that's the way that division works. Let's think about it using exponents. Well, I guess I did use some like perfect exponents here. So 3 to the third power over 3 to the second power, because 3 to the third power is 27, 3 to the second power is 9. Okay, and what this law tells us is that if we subtract the exponents from each other with division, and order matters here, it's what's on top minus the one on the bottom, right? So 3 minus 2, let's look, 3 to the third power minus the second power, there we go, equals 3 to the first power. And as we saw in our first rule, when this is a 1 here, that is equal to 3. Now let's think about what this means with variables. Let's create some higher level variables, because I'm tired of using these low numbers, even though they're faster to write. So let's say like we have x to the 7th over x to the 5th. Why not? What does this look like? X multiplied by itself 7 times. Well, I don't want to be a hypocrite, so I'm going to put that 1 there. But x, there's 3 x's, 4, 5, 6, 7. Okay, and then that's a really messed up looking line. Close enough. Okay, and then we've got x to the 5th power, so 1 times x, 1, 2, 3, 4, 5. And so what's going to happen? What do we do up here? We can cross out. If it's on the top and the bottom, we can cross it out, right? And so these 1s can go away. We're going to have 1 here. Probably use a different color. I just scratch them out like that. So for every one that's on the bottom or on the top, I can scratch it out. So I've gotten rid of 4. Okay, 5. All right, and now on the bottom, I'm out of x's, so I can't scratch any more off the top. So all I've got left is just this 1 down here, and I have 2 x's on the top. Well, what is x times x? That's equal to x squared over 1. Anything divided by 1 is just itself, so it's just going to be x squared, right? And what do we find? Look, x to the 7th divided by x to the 5th. So I'm just going to move up here, kind of ran myself out of room. X to the 7th divided by x to the 5th our law tells us that that's the same as x to the 7th minus the 5th, which is x squared, right? And that's what we got here, and that's what we got here. So even if you can't remember the rule, you can always just like break it down and do the logic yourself. Which brings me to this green color, which at first glance it doesn't always seem very obvious that x raised to the 0th power, and this x is just a stand-in for any number. Any number raised to the 0 power is equal to 1. And using what we've proved up here, we can actually prove this down here. So we said that if we multiply powers and we add the exponents together, so let's come up with a problem where we have an exponent of 0. The sum of the exponents is equal to 0. So let's say that we have 3 to the negative 2 power, and what would we have to multiply to make the exponent add to equal 0? Well, that would have to be 3 to the positive 2 power, right? So our law, our multiplication law here tells us that we're going to add the exponent, so that becomes 3 to the 0th power, right? Because negative 2 plus 2 is 0. But what are these numbers? What are these numbers? This, according to our negative inverted power rule, we've got 1 over 3 squared times 3 squared, and any number is just itself over 1, right? So 1 over 3 squared, that's 1 over 9, times 3 squared is 9, 9 over 1. And when we multiply fractions, we multiply straight across. So 1 times 9 is 9, and 9 times 1 is 9. And what is 9 over 9? What is 9 divided by 9? That is equal to 1. So provided that we follow the rules, follow the laws, logic it out, this 0 power, it should, since these are equivalent expressions, equations, 3 to the 0th power is equal to this 1 here, right? And we can do it with division as well. So let's say that we've got 7 squared over 7 squared. And the reason we're going to use the same exponent is because we're going to subtract them. So 2 minus 2 equals 0. So 7, 2 minus 2 equals 7 to the 0th power. But what is this? What is this fraction? What is it actually saying? 7 squared is 49 over 49, which, just like up here with this 9 over 9, that's equal to 1. So 1 is equal to 7 to the 0th power. And that's true of anything. So any number that you see raised to that 0 power is equal to 1. Alright, I hope that makes sense. Let's move on. Okay, good friend yellow. So what yellow tells us, oh, it looks like I made a little typo here. This M is not supposed to be an M. It's supposed to be, what is it supposed to be? Oh, it was supposed to be a little exponent. So x to the m. So this is what it's supposed to look like. It's supposed to look like x to the m power raised to the n power equals x to the m n power, where the exponents are multiplied together. So when you raise a power to an exponent, the exponents multiply together, right? Yeah, we can reason this out and see what we think about it. So if we have say x to the 4th power, right, in parentheses, and we're going to square that. I mean, what does square mean? Square means to multiply by itself. So if we have x to the 4th power multiplied by itself, that's the same as x to the 4th times x to the 4th. That would be x to the 4th squared. It's multiplied by itself, right? So according to the rule that we've already proven, already established, that when we multiply two powers together, the exponents add. So 4 plus 4 should equal 8. And that is exactly the case. That is exactly what we could expect, what we'd experience, because if we wrote this out, which might take a little while, we'd have two groups of x to the 4th, so x to the 4th times x to the fourth. And it's how many x's do we have? Well, we have 8 of them, right? And we can think about this with some real numbers as well. I like using 2 because it's just nice, easy bases here. So let's say x cubed, which we know what that is, x cubed squared. So what is this? If we use PEMDAS, or our order of operations, we know that inside the parentheses is what we're going to want to look at first. 2 cubed. So 2 times 2 times 2 we know is 8, and 8 squared. Okay, now we're outside the parenthesis. We're going to use our exponent. We're going to square it. So 64, right? So what is this? If we were writing it more in this sort of form, it would be 2 to the third times itself, 2 to the third, which is equal, so what is 2 to the third? That'd be 8 times 8. So hopefully this seems a little obvious when it's explained in this way. I'm sorry for the typo over here, but let's move forward. Let's go on to our nice orange color here. Okay. All right. This says that if you've got two numbers multiplied together, and it's raised to some exponent, that this exponent can essentially, I don't want to say distribute because that's a different property, but we can apply this exponent to each one of the numbers on the inside. So I'm going to do a brief explanation, and you're going to see exactly why that makes sense. We're just going to use the variables. Why not? So if I've got x times y, and I'm going to raise that to, let's do the third power. Why not? That means it's x times y multiplied by itself 3 times. So I can group this x times y, that's the first time, times x times y, that's the second time, x times y, that's the third time, right? So this is x times y cubed. X times y times itself 3 times. And what are we doing here? We're doing multiplication. And it is just a fact of mathematics that it doesn't matter the order in which we multiply. We can actually get rid of these parentheses if we choose to. And what does that give us? It gives us 3 x's and 3 y's. So if I wanted to, I could write this as x times x times x. Just rearrange the order here, times y times y times y, right? And x, if I make its own group here of x's and y's, x times x, well, that's x to the third power, and y times y times y, that's y to the third power. So what happened to this 3? Like when this was in parentheses, this 3, for lack of a better word, simply distributed itself to each term inside there, which is why I wound up with x to the third, y to the third. I'll leave that to you to prove with real numbers. I'm gonna move on. I'm gonna kind of show you that the same thing happens here in purple in this last rule. So let's do a similar example. So if I've got some division here, let's say x divided by y, and we'll go to the fourth power. Why not? So that x divided by y multiplied by itself 4 times. So that'd be x over y times x over y times x over y times x over y. So that's the fourth power. It's multiplied by itself 4 times, right? What's inside the parentheses 4 times. Okay? And when we multiply fractions, ratios, we just multiply what's on top and multiply what's on the bottom. So we can rewrite this as x times x times x times x over, sorry for the crooked line, y times y times y times y. And what is this? What is x multiplied by itself 4 times? That's x to the 4th power. And y multiplied by itself 4 times? Y to the 4th power. So there we go. This 4 on the outside of the parentheses is going to, for lack of a better word, distribute to both of those terms inside the parentheses. And this is why that happens. Anyway, I hope this was a good refresher of power laws, and I really hope that it helps you in the upcoming section on exponential models, and then also when we start getting into logarithms. This is going to be important. We're going to apply when we learn our logarithm properties. You're going to find that they're actually pretty much just mirrors, different ways of looking at these exponent properties. So it's good to keep these in mind, and if you can't memorize them, you should at least be able to rationalize them the way that I did here. Anyway, I hope you guys have a good day. I hope you enjoyed your lesson.